So basically, what is time series data? If this line represents the time, then here's some data and some more data and some more data. And all of these data points, all of these measurements are a time series. So measurements along time. As you can see here, they're evenly spaced. Now, if we add some more, they might be randomly distributed, but still they're time series data. So what is time series data? It's very simple. It's timestamps that are associated with data. So we have data that is attached to a timestamp. Measurements can be made periodically, as we've seen in the beginning, or in random intervals. And also what I think is important, time series data is append only, as we cannot travel back in time. At least I can't, unfortunately. I'm sure Uwe has other means than me, but I can't. Uwe, how's your DeLorean working at the moment?
Yes.
So for me, at least, time series data is append only, which means we can only add new data to the end of a data set as time progresses and we get new measurements. We do not modify past data or do updates on past data usually. And why should you care about time series data? Well, time series data appears in many applications, like Internet of Things applications, where you have sensor measurements measuring some physical capabilities. Also in monitoring and logging of cloud or on-premise solutions, every log message that you send can be viewed as a point of a time series data. And of course, also data like finance data is typically time series data because the stock market value doesn't change in retrospect. You only get new data appended to that. So as you can see, and that's only a very brief overview of some applications. There's many more that you can consider why time series data is important. And now the big question is, if we speak about time series data, there's a lot of very specialized databases and tools, and some of them I'll be introducing in a moment. And then we'll also talk about, or Uwe will mainly talk about, how can we deal with time series data in our well-known tech stack if we don't want this open sourcey geeky stuff that I love so much. So why do people even consider using specialized databases for time series data? And there's good reasons for that, because time series data, usually because you have very standardized formats, your measurements don't vary a lot. The values vary, but not the format of the measurement. If you measure temperature, you'll get a double precision number for each measurement you make. You won't get a string tomorrow if you're doing things right. So you'll have very standardized formats for your time series data, and that means you can usually compress the data very, very good. And the second thing is you typically have very, very similar queries that you want to execute on time series data. So what you want to do is retrieve a value at a certain point in time. So you want to know, what was the temperature in my fridge like yesterday at 10 a.m. So you want to retrieve a value at the point in time. You want to retrieve the current values. What is the temperature now? And you want to aggregate data over time intervals. You want to say, okay, what was the average temperature over the last 24 hours, or what's the standard deviation of the temperature over the last 24 hours? So you want to calculate aggregates on that data. And that's typical queries that you would run on time series databases that you would query time series with. Now, moving a bit more into the technology side, the question is, how can we store time series data in Azure? And I've come up with a few possibilities that we will talk about later. So one possibility, of course, is a Azure SQL database or managed instance, or a SQL server on-premise, or in a virtual machine, of course. The good thing is this is a really well-known tech stack, and you have experts like Uwe who can do black magic on SQL databases, on Microsoft SQL engine, and make things happen that you wouldn't think possible. And of course, if you look into Azure, those are available as platform services, so you don't need to maintain your own virtual machines or anything, which is also a good thing. The downside is, as in itself, Azure SQL database or managed instance or SQL server is not optimized for time series data, so it requires people like Uwe doing black magic who will tune that database to efficiently work with time series data. Second option is Postgres. Postgres with the timescale extension, and that's something that we'll look into much more later in this presentation, because that's a really cool tool set, and we'll discuss some of that and explain how it works later on. That's one of my favorites. I'll use a lot in IT projects at the moment. The good thing is it might not be as well known in the Microsoft community as SQL Server or Azure SQL or Managed Instance, but it's still a fairly well-known tech stack. It's available as platform service on Azure, and the timescale extension is also available for us on those platform services. So it's you can activate it by a few clicks. And the good thing is with the timescale extension, Postgres is optimized for time series data, so you won't need to do much more tuning on your database than just set it up and enable that extension. Downside is I've experienced problems with connection pooling, and I have to say that the timescale extension is very special with respect to naming of database objects. For example, uppercase characters are not allowed. And if you have uppercase characters in any column name or table name, then you will get messages that a certain column or table is not found, which is really weird because it's there. It's just a weird error message that took me about a day to figure out why it's happening. So this is really painful if you experience this the first time. So if you plan on looking into timescale extension, just remember everything lowercase, only underscores, and you'll be fine. Okay, what other options do we have? Well, the one option that people don't think about when you want to store time series data is storage accounts. And the good thing is they're very, very easy to handle, and they're very, very scalable. And they cost next to nothing, which is also for many customers interesting. The downside is, of course, then that there's no query engine running. They're not optimized for querying. And if you want to retrieve data from your storage account, it's a good idea to have some kind of data storage strategy. How do you partition your data to get the values that you need without reading all the data? Those are especially interesting when working with time series data, when you have when you use a tool like Synapse serverless pools, because they enable you to query files in a storage account with SQL, which is quite a cool feature. Not fast, not blazing fast, but it will work. It will do the job, and it will help you query data from a storage account at very low cost. Next option is Azure Data Explorer. We won't dive into Data Explorer too deep today, but Data Explorer is a really cool tool because it was specifically built for working with time series data. It was basically you've all used the backend of Data Explorer if you've ever used Azure Log Analytics, because there you have the Cousteau query language, and that indicates that Data Explorer is the backend for all the log analytics stuff that's happening in Azure monitoring. And so this is what it was built for. And you can, when you work with it, it feels very, very mature for time series data. Downside is you'll have to learn Cousteau. And if you have SQL guys like Uwe, they will not be happy about having to learn Cousteau, maybe. And the downside is, of course, if you want to integrate that into a solution, there's no real support for Entity Framework, and the upfront cost for running the smallest sensible instance of Data Explorer is rather high. So that stops some of my customers from using it. And there's other databases that are specifically designed for time series data that you will hear if you discuss time series data with customers, with colleagues. You'll probably hear the InfluxDB, which is a dedicated tech stack only for working with time series data that works really well. The downside is there's no managed service. So you'll have to run virtual machines. You'll have to configure everything yourself. You'll have to set up everything yourself. You'll find some pre-configured virtual machine images, but it still means you'll have to service everything yourself, which is not the way I prefer to use cloud services. And the same goes for Open Time Series Database, OpenTSDB, which is also very well-known dedicated tech stack for working with time series data, but again, not available as managed service, which is the downside. Okay, so now you've had a little bit of an overview of what you can do with respect to time series data, what's available with respect to time series data. So let's dive a bit deeper into timescale extension for Postgres, into Timescale DB. And have a look at that. So Timescale, as I mentioned before, is an extension for Postgres. So you install, the process is you install a normal Postgres server or cluster, and then you enable that extension, and then you can enable the usage of that extension for certain tables or databases. What's quite cool, it's very, very well documented. And the source code is available, which is also quite useful because you get to have a sneak peek into how features are working, which I find very interesting. And Uwe and I also looked at some of the source code to find out how they work, which is also quite interesting. And basically what it is, it's an extension for the relational engine. So they add some features to the Postgres relational engine, and they have some specialized SQL features, some specialized queries, some specialized indexes that they deliver with that extension. And now I want to dive a bit deeper into the timescale extension and go into some of the features. And the idea is that I will explain a feature that's available in Timescale database, and then Uwe will discuss what does that mean, how would that translate into the SQL Server world. So Uwe, are you ready?
Let's start.
Let's get started, okay. Okay, first feature is when you enable the timescale extension, tables become hypertables. A hypertable basically looks like a regular table, and the idea is that it's an abstraction to a standard table that basically consists of several individual smaller tables that store the data and that are called chunks.
Yeah, and this technology, so you all know that we don't have these technologies directly in SQL Server, but this is what Postgres is doing with the chunks. You can achieve this by partitioning, because that's exactly the same technology. So based on the construct, the chunks does only mean that we have for a dedicated time area, we have data partition, and that is something what we can achieve with SQL Server when we partition the data.
Yeah.
And another thing with the chunks, I think, is quite important to understand here. The chunks in Postgres are highly compressed. And compression in SQL Server, and I will show that later on in my demos, we have different options. The first one that we use, row compression, page compression. It's not very effective, but I think what you all know from from a perspective of compression is column store indexes. So these two technologies, partitioning and compression with column store, will be technology from the perspective of technology near to the chunks in Postgres.
Yeah, and what's more about the chunks? It's good that you mentioned this. Chunks can be configured so that, for example, recent chunks that you will access more frequently fit into the memory. So basically what Postgres does in the background is try to optimize those chunks so that they fit your hardware configuration as good as possible and give you a possibility to access the data in those chunks as fast and efficiently as possible. And indexes are built on each chunk independently, meaning that you can have different indexes for recent data where you would probably be more likely to retrieve point in time data, whereas for older data where you would be more likely to retrieve aggregated data, you would have other indexing strategies. Also, there is, and that's something Uwe already mentioned, compression. There's age-based compression, meaning that older chunks can be more highly compressed than more recent chunks, adding to CPU usage when retrieving data from those chunks, but making it faster to read them from disk when they're not present at all times.
Yeah, and to understand these kind of technologies in SQL Server, we have to build it with other features of SQL Server, because what SQL Server does not have. So when we partition in the background, it means that we have an index, a dedicated index from the technology side on every single partition, but it gets handled as one big index. So the technology, what Postgres here, the timescale extension for Postgres is doing, this is not achievable in SQL Server, but because we only have this one big index on it, so we cannot separate it. It gets separated when we use partitioning. That's absolutely fine. And another point, what can really bring bad experiences in SQL Server, what I never have seen in Postgres, is the inserts into this table. Because what you see here from the slide from Ben is, you see this helps ensure inserts to recent time intervals. So in SQL Server, when we have a clustered index, what I would normally not use in a timescale, in a timeline database, but a clustered index with a so-called ascending key has one big problem. When we insert massively data, and let's say we have a clustered index on the time column, then we will generate hotspots. And these hotspots are due to the fact that every single record wants to be inserted at the very end of the index. And here, to be honest, Timescale DB is working very proper. I've tested it with 1,000 simultaneous clients, because that is a normal thing when you think about sensors in a big building, Internet of Things. Yeah, so it measures the temperature and it's permanently hitting the database. And what I see then in SQL Server is the problem with this hotspot, that we have page contention, ledge contention on the very last page in an index. To achieve a better performance, you have to work with a trick. And unfortunately, what I would like to see in SQL Server is, I think that would be a really cool feature, is that we have, for example, in-memory tables, but not for the whole table, but let's say for a partition only. Because you all know that when we are dealing with in-memory, we do not have the problem with concurrency, because everybody can insert very fast. And so what I did then, when I tried to develop exactly the same feature as we have in Postgres, what did I do? I have my time series table, and I have a separate, in the background, an in-memory table where all the data gets pushed in, so no more ledge contention on it. And when we have, let's say, 1 million rows, then I push the data directly into the partitioned and the partition table with column store index. It gets immediately compressed, and then I have the data in. But it's not so efficiently as it is in Postgres, to be honest.
So you're wishing for optimized chunks.
Yes, yeah. So what I would really like to see, what I really like to see, maybe in 2030, is that we could have tables in SQL Server which can combine both a persistent part and the in-memory part. And that the in-memory part will automatically, let's say we have a threshold what we can configure the table with. And when we say, I want to have 104,000 records in the in-memory portion, when it hits this threshold, it automatically moves over to the persistent table. Would be a great feature, but
would be a dream come true.
Yeah, maybe.
Okay. Now
I think when it comes into SQL Server, I think that I will retire. No, I won't get retired. I will work for a lifetime.
Make space for the younger generation.
Yes.
Yeah. So the next thing that the timescale extension does is that hypertables are not just chunks on a server, but they can be distributed. So basically what Postgres can do is scale out of those chunks, which is quite nice. If you have a multi-node installation, then it will automatically distribute the chunks across the different data nodes for better performance when querying multiple of those chunks.
Yeah, this is unfortunately the feature we don't have in SQL Server. Whether in managed instance or on-prem, we had it with a big data cluster, but we all know it's
rest in peace, big data cluster.
But I do not have very much experience with Synapse, but maybe Synapse will have this feature then.
I think this would be possible to achieve with Synapse dedicated SQL pool, where you have a distribution of your tables as well. Then you would need to find the right distribution function, a good hash function for distributing the table, and then it should be possible there as well.
Yeah, what we can do in SQL Server is only we have the feature of partitioning, and we could distribute it on-prem on different storages, but that's not the same.
Yeah. Okay. Then Uwe already talked about compression of chunks. So basically, you set you configure your hypertable. You can configure a hypertable for compression, and then set up a policy when you want which chunk to be compressed how. And you can even compress chunks manually as they age. So you could say, okay, if my chunk is older than X, then add that compression already. Ventured into that feature in the beginning when we first talked about chunks. Only wanted to mention that this is a feature that is available in Postgres timescale extension as well. Next feature I would like to talk about, if you think about IoT data, sensor data, and you think about queries you run on that data, usually you're not interested in data that's 10 years old, not in the raw data. You'll probably store some aggregates, some averages, but like if you have sensors that report temperature every minute, after like a week, you'll probably not want to look into that on the minute scale, but rather on the hour scale. And then after a month, you probably look on a daily scale, after a year on a weekly scale, something like that. So you'll have some, you can get rid of the raw data of the full resolution of the data. You would of course keep that in some cheap storage, but in the database, you could probably get rid of the raw full resolution data after a certain period of time. And that is called data retention. And that's also something that's available in Timescale, is that you can configure, you can implement policies, configure policies that will remove old chunks as you progress in time, which ensures that your table doesn't grow infinitely, because this, especially in the cloud, is always a cost question as well. So you would also try to get rid of old data, and the timescale extension has a feature for doing just that.
Yeah, and this is unfortunately something requires, for an optimized deleting, from my point of view, if you do that with a managed instance, or if you do that with an on-prem SQL server, the deletion of data, especially when we talked about timescale or the timeline databases, is that we normally will delete a huge amount of data. So let's say 1 million rows from 10 years ago and all this kind of stuff. And we all know when we delete data from a database in SQL Server and it hit the threshold of around about 5,000 records, then we get a table lock. And a table lock prevents to insert other data coming from the sensors or from financial data, whatever. So if you want to have a good working data retention, it is necessary, it's mandatory to have partitioning activated. Otherwise,
exactly.
it won't work.
Because with partitioning, you would just switch out the partitions you don't need anymore.
exactly. And what you can do is you can truncate partitions. So if you would like to have a rotating system, for example, because you don't want to have too much partition, then it's easy to truncate a partition. Really cool.
Yeah, cool. So basically, since the timescale concept also works on chunks that you would use for data retention that you would delete, that would actually be the same concept if you do that on a partition level. Okay, finally, what timescale also does, it gives you a possibility to continuously aggregate your data, meaning that you can set a kind of view that continuously aggregates data. If a new row comes in, then the new average is calculated and stored in that specialized aggregate. And then that will be materialized and stored in the database. And that's cool if you have like queries that you run frequently that ask for calculation of averages or something, that you'll have all the data handy just as the data flows in. And that's also a nice feature that I like to use with timescale databases.
When you say continuously, does it mean that it goes automatically into the so let's say you want to have, let's say, in a 15-minute range, and you're permanently asking for 15-minute ranges, that when new data come, they will get automatically compressed into this 15-minute window?
Well, what happens basically is that a second table is created that contains those 15-minute aggregates then.
Aha. Okay. Yeah. Now I understand this, because this is something what SQL Server can do in the same way. But what I think is maybe in a little bit better way. And therefore, in SQL Server, what we have is, or maybe you're talking about this materialized views, which is the name in Oracle Postgres. But in SQL Server, what we have is index views. And the good thing with the index views, from my point of view, it's a pro and a con. But when you have index views, they get updated automatically with every single record you insert into the base table. This could be a pro, because then we have immediately the actual data. But there is a massive negative point in it. Think about inserting data. What we want to do is we want to insert very fast the data into the table. So it all depends on for what it is used. And when it needs to update all the index views around in 15 minutes interval, 30 minutes, 1 hour, 1 month, and so on, they all need to be updated in the same way. So the transaction takes longer and it's bigger.
Yeah. Okay, so we've discussed some of the features that are available in Timescale and discussed what they would be like, what you could use to implement them in SQL Server. So let's have another look have this all in one glance. So hypertable basically becomes a relational table, Uwe.
Yep.
Chunks turn into partitions.
That's the technology behind here, yeah.
Yeah. The difference is that Timescale can do partitioning on multiple attributes of the table.
Yeah. I wish you could do this the same way. Yeah, this is really a cool, an absolutely cool benefit, which I would really like to have in SQL Server. But in SQL Server, you just only can have one dedicated partition key. Or what you can do is you create a partition key by your own, which is, let's say, by date and sensor, for example. But to be honest, no.
Yeah.
No.
Then,
yeah, have to say.
Yeah. Well, it's just different. Then you have the compression of the chunks, which you turn into the native compression, of course, row or page compression, and column store indexes.
Yep.
For compression, which is also cool. You have the materialized view with the real-time aggregations that would then turn into index views. And you have the data retention, which we discussed you would do by partition switching and would configure by using SQL Server agent jobs.
Yeah, only way.
So basically, those are the key features for timescale extension, and we've discussed on how they would look like in SQL Server. And Uwe, I think it's time that you take over and share your screen and show how these can be implemented and what the results are.
Yes, okay, I do so. So here we are.
Because that's the bit we're all excited about, right?
Yeah, people want to see data in action. Okay, so this is my test data. What I have a table here. Before I go to this, go on with this slide, if you want to have all the demos, the original database, what I'm using for, what you can do is just follow this link here. It's t1p.de timelines, or here the QR code for that you can download the scripts, and inside the scripts or the PowerPoint you will find the download link to the database. Okay, so this is my table. I have the datetime column. I have a so-called time zone shift, city name. I do it with cities, and the workload is as follows. Every single city will report once in a minute the temperatures, the cloud, the rain, all this kind of stuff, and that gets stored in a database. So what I have here then is, and I have to be really in the same way, I have to work in the same way as Postgres or Oracle is doing, and hopefully we all know that Postgres and Oracle do not know the concept of a clustered index. So both technologies are normally working with heaped tables. So I have the time, the city name, and the weather type, which makes every record unique. And it looks like this. So we have the time, we have the city name, and we have the weather type ID for whatever it is. I downloaded the example files from the web. And my database has originally 267 million rows. So that's only for fun, okay? That we have a little bit fun.
Yeah, that's only
here
a toy
for
database,
this
right?
session, I have reduced it to only 3 years, because otherwise the index creation, the partitioning, and all the kind of stuff would take too long. So that is the reason behind that I have a smaller set of data. But if you download the timescale DB, then you have all the data inside and you can play around with this. Only requirement is you have to have at least SQL Server 2016, otherwise you cannot use this. Okay, so what I did was I was first of all doing some benchmarks, show the average temperature for Austin, for example, for every 15 minutes, and so on and so on. I don't want to show you boring slides. I want to go into the fun part, and the fun part is this. So let me start here. With the first query, what I'm doing, so you see here's my timescale DB, and all good developers know this. We don't want to have the number of rows shown, and we want to see how much I/O do we produce, and for us, or for me, it's way more important, how much CPU do we consume. I go into my timescale DB, and the first thing, or the biggest problem for us is, and I want to show it here for you, is how can we create these time buckets? Because we need to have buckets, put the data from this bucket, which fit into this bucket, and then we can do some funny aggregations over it. So the problem here is, how can we achieve this? And the good thing is SQL Server 2022 has a bright new feature. I like this feature. It's very cool. So first thing, how can we achieve
Uwe,
this?
maybe we should mention that
Here's the very first query.
Uwe,
yeah.
Maybe we should mention that this is, of course, also available in Postgres timescale. The time bucket
sure.
function.
Yeah. But this is in the extension. There is a generic function in it, which we can use to create these buckets. Not the calculation, but the buckets. I come later on to this here, and maybe, Ben, you will have the time to show it then afterwards, maybe in Postgres. Here comes the very first query, absolutely primitive, very simple. And this is something where we do not have any problems concerning building buckets. I want to have for every single year the average temperature by city name. And it's only for 2019. So I expect to get back 10 or 11 rows. Let's see how SQL Server is dealing with that. You see that it takes a little time. Here we just only have 12 million rows, but let me hide this. It took 5 seconds. To be honest, for a full year, not so bad. So this is the average temperature. And when you go to the messages to see the I/O, then I see two things what makes me a little bit nervous. The first thing is the scan count. The scan count 9 does mean I have an 8-core machine that this query was running in parallel. And we were consuming around 58,000 data pages, which is 50 megabytes. And then we look to the execution plan and we see how it works. We make a full scan with all the data, 5 million rows. Then we do we extract the year. This is the compute Scala, and then we do the aggregation, and we give the data out. This is the sort operator. That's easy. Compute Scala, and that's it. Easy. How can we solve the next query? The next question is, give me the last 60 minutes for Austin. And yeah, we have two approaches here. What I was taking the solution with the CTE. So what I get is the very last temperature measure I get. This is here the last number. And you can see here that SQL Server is very efficiently with this. We have an index here on the time and on the city. So we can use an index seed. We give the very first, make an aggregation, what is stupid because we just only have one. However, that's okay. And then the only thing what we then do is we add minus 59 minutes and we get the list of the last 60 minutes. And that goes really quick. SQL Server can use the index. That's fine. You see the read lookup. That's okay because excuse me, I have to smoke. The reason for the read lookup is very clear because we have a non-clustered index, so we have to look for the temperature in the table itself. And here comes the first challenge. Have a look to this one. What I want to have is for the 1st of April 2021, for 1 hour and 15 minutes from midnight to 1:15, the average temperature, but not for every minute. I want to have it for 15 minutes, so in intervals of 15 minutes. To build intervals, and if you don't have SQL 2022, you have to do that with CTEs, a common table expression with a recursive CTE, which means that we create the anchor. This is this one, and then we refer permanently to this anchor again and again and again. Let's see what this will bring us here. So let me say I want to have for around 1 hour, 1 hour 15 minutes for Austin in 15-minute buckets the temperature. The first thing what I want to get out is the buckets. So this one I can create with this query. It's only the buckets. You can see here now that I have now the starting point and the end point. So this is the interval what we need to search the next query for the average temperature. But that is easy. You all know how to work with cross-apply. So this is the query, what I'm using that. It looks complicated, but believe me, it is not so complicated. Let me make it a little bit smaller that we can see better the code.
Uwe,
yes.
If you have to decrease the font size to show the full query, it is complicated.
I know, but yeah, but here you see, it is, so I think Isaac Ben-Gan told, as longer your query is, it is an indicator as better it performs. So yeah, it is a problem here, but you see that I have now my CTE here called dates. And what I'm doing then is I take the dates, and for every single date I get here, it's 4 or 5 information. I then run a select on the weather data. I want to have the average temperature, which is in this time range, and for the given city, Austin. Let's run this query and see how long this takes. By the way, one problem with the CTE, it has an automatic limiter. That it means for iterations, when we go into a CTE and into a self-referencing CTE, it stops automatically at 100 recursions, and then it stops, say, limit is reached. So the max recursion 0 does mean that it goes endless. The query trace flag here is not so important. I just want to show you the pushdown predicate, what happens. But what you see here, keep in mind, we only have 5 records. The query was taking 6 seconds. 6. And maybe a few of you mean, well, yeah, that's not too bad. But think about this. The problem with this query is, or the query is running so good only because we have not so much data in it. We only have 12 million rows, and the original one has 267 million rows. And that does mean that the SQL Server will go 4 times through the whole table. And that brings us to the problem. You see here the pushdown predicate that it say, well, the time, this is a range, what we are looking at. Rangers are bad from the perspective of querying. So what we did here was we were going 4 times into the weather table, 2 times from the index, 4 times or 5 times for the retrieving of the data, and 1 time for the index seek for creating the CTE. That's not really cool. That is not the best way to handle it. So this is the base query what SQL Server is doing. Yeah, so this is what is in the cross supply. We are looking for just only for 15 minutes and see what SQL Server then is doing. You see that it takes very long. It is 1 second for just only 15 rows. But SQL Server is doing an index seek over, and that's the problem, everything what is in this time interval. Because, keep in mind, the time at the very first part, the very first column in the index, and then it comes to the city. And what we can do is, to achieve a better performance is, yeah, let's create a better index on it. Yeah. So you see here, this is what you have to justice about. Is it better to have it on the time first, or is it better to have it, in this case, on the city name first? Because think about this. Oh, it already exists. Okay, good. Then it should work now. 1 moment. That's live. I want to make sure that I really have this index. So again, we come again to this query, and now it's creating the index. It's so cool. Yeah. Okay, done. And Ben, now you see why I have dropped so many rows here. Otherwise, we would fill the 60 minutes with, is it ready now? Is it ready now? Yeah. But again, it takes 5 seconds, not so good, not really good. Yeah, and we see that we also have the same problem. We make a seek on the city, but the problem is that SQL Server in this case cannot handle properly the range scan. And therefore, we have a cool feature called Date Bucket. Date Bucket is a feature in SQL Server 2022. Ben has mentioned it. Is it the same name of the? No, it's named a little bit different in Postgres, I think. No? But let me show. We do run the same query again. 5 seconds.
In Postgres, it's Time Bucket.
time bucket. Okay.
Yeah.
So, and see this. Bang. Less than a second. Yeah. The execution plan showed that it goes way better. It's performing way better than it has been done with this CTE. And the aggregation is now inside, and you look to this. That is really cool. So when you're dealing with time series, I, from my point of view, can strongly recommend try it out in SQL 2022 if you want to go to SQL Server. So, but this is only one thing. Do you want to mention something, Ben? So far, anything?
No,
what is
no.
better
So far,
in Postgres?
no. I think it's actually comparable. Okay. If you use the specialized functions, then the query engine will know what to do.
It is highly optimized for this. Yeah. So, okay, now I want to go with you step by step through the different technologies, what Timescale DB has built in, what we have to do in SQL Server. First thing is the data compression. The data compression, this is what the chunks are. They are highly compressed. And let's first of all try to do this with page compression in SQL Server. Here's again the query. Yeah, I run this. You see that I don't use the date bucket function here. I want to do it with the CTE. So here is the query. What I want to see here is for a full year. You see it here. I create the CTE for 2019 for every single month. And I want to have for every single city on a monthly base the average temperature. And it takes time, and it takes time, and it takes time. It's a huge amount of data. Yeah. So around 5 million data are now processed here. Here we are. It took 14 seconds. To be honest, if you want to have it for mobile data, for a report, something like this, this is not acceptable. Definitely not acceptable. And in Postgres, to be honest, this is incredibly fast. I have to agree to this. So you see what huge amount of data we are processing here. These are lots of gigabytes. And see this. It was a heavily CPU-based process here. And the I/O makes me a little bit nervous. So let's try to make it a little bit better. So I have prepared everything because otherwise it would take too long time. Refresh. And you can see now here that I have all the tables, one with compression, one with partitioning, and so on. So you see that this part, whoops, come on, is now processed. I have created it. So here is the query. I have made a primary key on the time, on the city, and on the weather type, and with the compression on. So I took the page compression, which gives us approximately 30% of compression rate. But there is a con against compression. Maybe you all know compression does mean that the data will not be compressed in memory. Before they go into memory, they have to be decompressed. So we are dealing with CPU again. We do not solve the problem. This is what I can say here. Again, the same query, but now you see it here on the compressed data. Let's see whether we are a little bit better. 14 seconds are to beat, but I think, 4 seconds. That's not too bad.
And let's again, Uwe's doing black magic.
This is black magic. Yeah. And you see it here. Yeah. So SQL Server read the data from the data page, get it into the memory, but in total, we have only a little bit of I/O here. So we reduced the I/O, and as less I/O we have, as less CPU we are consuming. So in total, we have 16 seconds. The elapsed time, 4.8 seconds. It is better, but to be honest, it is not okay. For me, if I think about this, you're staring at your report and you click refresh, 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 especially when you're in the financial markets and you want to see how the asset is going up and down, and you click refresh, 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 and it takes 4 seconds. Oh my goodness, no. I was working in an investment bank. I was a SQL Server architect there. Believe me, they are not really friendly to you if their system is hanging. Yeah, so this is the way how it was with the compression. But let's see whether we can do this in this way. Let's see how long it takes. What I create now, I create a non-clustered index because that's smaller than a clustered index. I only have the time and the city name in it, but it's not compressed here. So time, city name is in the index, and the temperature is in the leaf level. So that means that we have very much less, that we should have less I/O. Let's check it out and let's see how good it will perform. Keep in mind that the index is not compressed. Here we normally have to have less data, have to read less data. You see, we are now in 3 seconds. This is 25% less. Not bad, but look to the I/O. Yes, we are a little bit better. From 31, we are down to 25. And let's see, let's make timescale great again. We now create exactly the same index, but now with compression. 3 seconds are to beat. And you will see that the index creation will take a little bit. The reason here is that is highly CPU, what now gets consumed, because SQL Server has to go when it deals with storing the data on the page, that it has to compress it, and that's CPU based. So give it a little bit time. In the meantime, while it is running, I scroll down and I will run this query again, exactly the same query. 3 seconds was it? And let's see whether we are better. But you see, no. 4 seconds, 3 to 4 seconds. The key point here is we have really less. We have reduced it by 50%. That's cool. But the problem is that SQL Server needs to decompress it when it reads the data from the storage. So there is always a pro and con. And if you have these kind of indexes, when SQL Server inserts new data into this index, keep the following in mind: the data will not be compressed on the data pages. If you want to have compression, you have to rebuild the index. Yeah. So this is one thing. So compression, the classic way, might help a little bit, but in general, it will not help to speed up the query. In general, it will be a better feeling for you, because then Ben has mentioned it. What is it expensive in cloud? The services, the storage, or as big as your database is, you have to pay more. So if you compress it, it might help a little bit to save money. But what about data partitioning? Data partitioning can help you really much, because then we have the so-called partition elimination. So we have here 3 years. Oh, 5 minutes to go. I need to hurry up.
That's what I was trying to say. 5-minute warning.
Yeah. So you see, I only have 3 months here. So what I created now was I created a partitioning function. 2019, everything goes up to 21 to the next. And then I have a table called partition, where the data, you see here, that this one is on the partition function. So we divide it every single year. I create my clustered index, and then I insert the data. And it's how the data are distributed. And you can see here that we have around about, for 2019, we have 5 to 3 million rows in it. This is 21, not so much data, but that's okay. In total, we have around per year, 5 million rows. Let's see how it works. Here's the query again, and we go for 1 year only. One of the problems we have here, unfortunately, is this one. With this one, we hit the second partition. However, let's check it out. Go for this. And we think that it is better, but 3 seconds. What is the key point here? The problem is that normally SQL Server will eliminate partitions. But one moment, I don't see it here. Partitioned, whether data do. One second. It's in, okay. Why don't we see the partition? One moment. Once again. Normally, I would expect here partition elimination, but it will here not work. You see that we have 73,000 IOs, lots of IO here. But let's see how it works when we compress it. Oh, come on. Now I make, oh, no, stop. Okay, come on. Sorry, takes a little time. Okay, now I have created an index, again, on the partition, but what doesn't help here is the partition key. That is exactly the problem I have. Because the first part of the index is now the time again. And you keep in mind, remember, the equal predicate should be first. Let's see how this works. Whether it is a little bit better, but it isn't. It doesn't work here really much. So we always have to go a little bit more into details with this, how we can improve this. The only thing what happens is that we have less logical IOs, but that's absolutely okay because my index is smaller. And I want to go to the last point because 2 minutes to go. What Postgres has, so partitioning, a column store and column store partitioning, I can promise you it will not help so much here. It will reduce the IOs, but it will not help here very best. But what helps is this one. And this is what Postgres has the same way. What Postgres has is called materialized views. And you know, we have this as index views. So I have I created this one. You see this one here. This is, I created the schema dates. And this is my table. What I'm doing here is I'm pushing all my information into this dates table. I only wanted to have it for 5 years. That comes from the bigger one. And then what I did was this here. I create a view. You see here that I created the table based in a 15-minute interval. Yeah, so we do not have so much more data in it. I created an index, a clustered index on the date from date to on the table, and then I created this view here where I do my aggregations. That's a question, but yeah. And what I do then here is, and this is really cool, I love this, is create an index on that view. And in this moment, you materialize the view, you make the view internally like a table. And when we then run queries against the table, so there's a view, but see how incredible fast it is. Yeah, and look to the IO. And this is what I really want to, that's impressive. Here, come on, so, and go for it. So, what is this? What's going on here? It's normally, you see that it took 7 seconds. This is not true. This is not true, no. Because it only takes 4. You see, Ben, this is live. This is action, unfortunately, but it should be. There is something going unfortunately wrong. I need to check it, but believe me, this will really help you. Let's see whether it is. Material weather data month. No idea.
So basically, what we can see is that if the
it takes much amount to achieve this. Okay.
Yeah.
Yeah.
That if we have pre-aggregated the data, things will be much faster.
That is the point. Yes. So and this is what Postgres is doing the same way. Yes. I'm very sorry that the last example didn't work. The last demo didn't work. I'm really sorry about this. But in the slide deck, you will have all the links, and you can follow them and download
and Uwe, we will both follow up on all these topics. I think this will not be the last presentation we give on this topic.
No. And what we are planning, we can say, I think, then, if it's okay.
Yeah, sure.
We want to make, Ben and me, we are dealing with the idea to make timescale DB functionality as it is in Postgres as an extension, like an extension in SQL Server, that we have it in SQL Server the same way. Good.
Yeah.
Do we have any questions?
I answered the question, was if we have considered in-memory OLTP. You already talked about that in the beginning of the session.
Yes.
So I think all that's left for us is to say thank you to all attendees for attending our session.
Yes.
It's been a pleasure to be here in this event. Uwe, it's always a pleasure to present with you.
I give it back to you. I love it to present with you. Very good team.
It's very enjoyable. And I think to sum things up, what we can say is the Postgres timescale extension is really good. It's really well done, well crafted. And it's really exciting to look into what it has to offer and how we can bring features from that to SQL Server.
Oh, yeah.
There's a lot to learn here.
And I don't like it to say, but I have to say, the Postgres solution is incredible fast. That's really incredible fast. And we are working on it to make SQL Server fast again.
Yes.
Okay, good.
Thanks a lot.
Then we're done. Thank you very much. Have a wonderful
Thank you, Ben, and thank you, Uwe.
And enjoy. Yeah. Thank you. Bye-bye.